Hello, I am Seema and welcome to part 15 of the chapter Hydrocarbons. We have studied about alkanes. Let us now study about the alkenes. Alkenes have a general formula CnH2n. And alkenes may be defined as hydrocarbons that have at least one carbon-carbon double bond between them. So we say alkenes are unsaturated hydrocarbons. They contain at least one double bond between any two carbon atoms, and they have a general formula CnH2n. The general formula for alkanes is CnH2n plus 2. It means whatever is the number of carbon atoms, the number of hydrogen atoms in alkanes is twice of that plus 2 more. So if this is 2, this would be 2 into 2, which is 4 plus 2, that is 6. But in alkenes, the general formula is CnH2n, which means that it has 2 hydrogens less than the alkanes. That is, if this is 2, then in alkenes, the formula would be C2H4 and alkane would be C2H6. So an alkene has 2 hydrogens less than an alkane. That is something that we know just from the general formulae. Let us now understand why are these 2 hydrogens less and what is the difference between those alkanes and alkenes. This is the simplest alkene. For an alkene, you need at least 2 carbon atoms. Why? Because there should be a double bond between 2 carbon atoms. So in alkanes, we have the first member as methane, which has only 1 carbon atom. Because all bonds should be single bonds, and therefore the alkane that has the first member of alkanes can have only 1 carbon atom. But unsaturated hydrocarbons come with the definition that there is a double bond in alkenes, and in alkynes we say there is a triple bond between 2 carbon atoms. So you need at least 2 carbon atoms, a molecule which has at least 2 carbon atoms. So your first member here would be one which has 2 carbon atoms, which is known as ethene. Now if I compare ethene to ethane, what is the difference? I told you that this is in ethane, it is C2H6. And take a look here, this is C2H6. Every bond is a single bond. The 2 dots represent a bond. The 2 dots are actually the shared pair of electrons. Each atom which is bound by a covalent bond is contributing 1 electron, and these 2 dots, this dot belongs to hydrogen, this dot belongs to carbon. And we believe that this bond, this is the shared pair of electrons which results in a single bond. In methane, the carbons are sp3 hybridized. You know this. And the shape is tetrahedral. The shape of this around the carbon atom is tetrahedral. And that is how the molecule expands in 3 dimensions. In alkenes, the difference is that 2 hydrogens are less in it. So let us assume that these 2 hydrogens leave. So if the 2 hydrogens were contributing 1 electron each to the bond. So if these 2 hydrogens leave with their own electrons, you are left with the carbon with its electron and this carbon with its electron, and this electron which is left, it forms a bond with itself between the 2 carbons, resulting in a double bond between the 2 carbons. And since it has this double bond between the 2 carbons, these 2 hydrogens can no longer be bound because they were using these 2 electrons to form the bond. So the 2 hydrogens leave, and now what you are left with is carbon-carbon double bond and 2 single bonds with the hydrogens being formed by each carbon. And that is the alkene. And that is why the alkene has 2 hydrogens less than the alkanes. Because wherever you have that double bond, the 2 hydrogens will leave there and result, and the electrons, that carbon's electrons, they share that electron with each other, resulting in the formation of a second bond. We also know that the first bond between 2 atoms is a sigma bond. A sigma bond is formed by the head-on overlap of orbitals. That is, whatever the orbital is, like if these are p orbitals, they will, and imagine it to be p as a dumbbell here. So if these are 2 p orbitals, they will overlap head-on, headways like this. right? And a pi orbital, that is a second bond, is always formed by the sideways overlap of the p orbitals. So it is a lesser portion is being is overlapping, and therefore the second bond is a weaker bond. The first bond, since it is head-on, the collision is head-on, the overlap is also greater. The entire lobe almost could overlap, although it doesn't, but yet the area of overlap is larger. I could draw this and make you imagine it, that if there is a head-on, take a look here. The head-on overlap is, the area of overlap is larger. But when the same two p orbitals are overlapping sideways, the area of overlap would be much lesser. Do you see? This is very little overlap. But the first overlap has a larger area of overlap. So the first bond is a sigma bond, while the second bond is a pi bond. Now, alkenes are also known as olefins. Ole is for oil. They are oil forming. So they are also known as olefins. And why are they called olefins? Because this first member, that is ethene, when we made it react with chlorine, it resulted in the formation of an oil-like substance, a liquid which was an oily liquid. And this oil-like liquid gave us the feeling that olefins or alkenes are compounds that produce oil. And therefore they are also, in common nomenclature, we also call them olefins. Now, what is the structure of the double bond? In order to understand the structure of the double bond, we again have to go back to the hybridization. Carbon has what is the electronic configuration of carbon? Carbon is 1s2, 2s2 and 2p2, right? Now, if we say it is 2s2, 2px1 and 2py1, when it has to form bonds, when it has to form single bonds and the sp3 hybridization takes place as in alkanes, the s orbital and the 3p orbitals, that is 2s, 2px, 2py and 2pz. These four orbitals, they redistribute their energies and result in the formation of four hybrid orbitals. The electrons, two electrons in s, one of these electrons jumps up to the empty p orbital, and all of these now have single electrons. So 2s has only one electron, 2px has only one electron, py has one electron and 2pz has one electron. Now all four orbitals have one electron each, and they redistribute their energies and result in the formation of four equal orbitals, which are known as the sp3 hybridized orbitals. Now these sp3 hybridized orbitals, they orient themselves along the four corners of a tetrahedron, and that is how you get the structure of alkanes. Like in the case of, I showed you in the previous two videos, I have shown you the structure of methane, ethane. So if this is the central carbon, it results the four sp3 hybridized orbitals, 1s and 3p orbitals, they form four equal orbitals, which forms a very symmetrical structure. In the case of olefins or alkenes, on the other hand, the carbon does not undergo sp3 hybridization. Excuse me. Alright, so I was saying that in the case of alkenes, the carbons that have the double bond between them, they do not undergo sp3 hybridization, rather they undergo sp2 hybridization. That is, one s orbital and only two of the p orbitals they hybridize. One of the p orbitals does not participate in hybridization. Now, when you have four symmetrical hybridized orbitals, they occupy the four corners of a regular tetrahedron, the structure that I made and I showed you, that they will form a tetrahedral arrangement like this, right? But in the case of alkenes, what happens? The two p orbitals and one s orbital, they hybridize and they result in the formation of sp3 hybridized orbitals, which occupy the three corners of a triangle. And the angle between them is 120 degrees. In sp3 hybridization, the angle between them is 109 degrees 28 minutes. But this becomes 120 degrees. So these three, they occupy the three corners of a regular triangle. And the unhybridized orbital remains perpendicular to this plane, like this. It remains perpendicular, that is, if this is a p orbital, one lobe will be above it and one lobe will be below it. Now what happens, the two carbon atoms, both the carbon atoms have this structure that both of them are forming this triangle. Both of them are forming this triangular sp2 hybridized structure. Now, yes. Now one of these bonds, it overlaps and forms the sigma bond. That is the first bond between the two carbon atoms, right? One of them forms this, these form bonds, the other two sp2 hybridized orbitals, they form bonds with hydrogens. And the one of the sp2 hybridized orbital, it overlaps and results in the formation of a sigma bond. But what about the pi bond? The pi bond is formed by this overlapping, this orbital which was unhybridized. The unhybridized orbital is kind of perpendicular to this. And since it is perpendicular to the plane of this paper, you can imagine one lobe is going behind the board, one lobe is coming in front of the board. These overlap sideways and they result in the formation of the second bond, which is the pi bond. The first bond was the sigma bond, which was formed by the sp2 hybridized orbital. The other two sp2 hybridized orbitals formed bonds with the hydrogens. But the second bond is formed by the unhybridized p orbital and by the sideways overlapping of the unhybridized p orbital. So by the sideways overlapping, and that results in this second bond. The second bond is weaker because of the sideways overlapping. And remember, hybridization also imparts a kind of a stability to the molecule because it gives more symmetry. And this orbital is unhybridized. It has not participated in hybridization. So that is the structure that you have of alkenes around the two carbons that have the double bond. So we say, what is the structure of the double bond? The carbon-carbon double bond consists of one strong sigma bond. It is strong because there is a head-on overlap. One strong sigma bond which has a bond enthalpy of 397 kilojoules per mole. The first bond, the first sigma bond, has an enthalpy. Enthalpy means it is the bond energy or bond dissociation. If you have to break this bond, you will need 397 kilojoules of energy to break the bonds of 1 mole of these first sigma bonds between the two carbon atoms, due to the overlapping of one of the sp2 hybridized orbitals between the two carbon atoms. And there is one pi bond. The one pi bond is formed by the sideways overlapping of the unhybridized p orbital, and its bond enthalpy is 284 kilojoules per mole. From the magnitude of the bond enthalpy, you can know which is a stronger bond. If there is a strong friendship between two people, it is difficult to break that friendship. So you need more energy to break that bond if the bond is strong. But if the bond is weak, you will need lesser energy to break the bond. So the first bond being strong, you need 397 kilojoules of energy to break the bond of one. Let us imagine it's just one bond or 1 mole bonds. And for the second bond, you only need 284 kilojoules because it's a sideways, it's a weaker bond. The second bond is a weaker bond. And it is formed by the lateral, that is the sideways overlapping of the bond. In alkanes or even in alkenes, if there were other carbons where there were carbon-carbon single bonds were there, the bond enthalpy between a carbon-carbon, if there is only a carbon-carbon single bond, the bond distance, what would be the bond distance? The distance would be 154 picometers. Now what happens? the distance between these two carbons will be 154 picometers. But when you have the first bond is 154 picometers, because there the hybridization is sp3 hybridized. sp2 hybridized orbitals are shorter than the sp3 hybridized orbitals. So the first carbon-carbon single bond also will have a lesser distance between them. So the first bond, if there was only a single bond, the distance would be 154 picometers. It means the hybridization is sp3. But if there is a double bond, then the first is sp2, which itself is shorter, and on top of it there is a second bond which is still bringing the two carbons closer. So the bond distance for a second, that is for a double bond, carbon-carbon double bond, is 134 picometers. If there is a double bond, the distance between the two carbons will be 134 picometers. Which means that whenever in alkenes the two carbons are closer, the closer they are, and then they have two bonds. So it will be more difficult to break a double bond than it is to break a single bond. If you totally want to separate the two carbons, you will need more energy because these two carbons are one, they are closer. Second, the energy that is holding them together is, or that was released when the bonds were formed, was greater. So you will have to need twice the amount of energy, that is the energy required to break the first bond and the second bond to completely separate the two carbon atoms. Now this is if you want to separate the two carbon atoms. On the other hand, if you really look at these two bonds and you compare their energies, the first sigma bond is strong, but the second bond is weak. So it is possible to break the second bond. You may not break this first bond and you may not really separate the two carbon atoms completely. But in alkenes, the second bond is weaker, which makes the second bond a site for attack, because that's a weaker link. There is a possibility for that bond to break, and if it breaks, what is a bond? It's a pair of electrons. So these electrons can be made available to any species that needs electrons, because these bonds are not very strong. These electrons are not very strongly bound. The second bond is weak. So there is a possibility to break this friendship. So any compound or species that needs electrons will come and attack this second bond. And what is a species that needs electrons called? It is called an electrophile. So you will find that electrophiles will come and attack this second bond in alkenes. And let me just read this now. Since the pi bond is weaker than the sigma bond, the second bond, the pi bond, is weaker than the sigma bond, alkenes behave as sources of loosely held mobile electrons. So they become the sources of, since the second bond is weak, these electrons are not strongly held, they are loosely held. And these electrons can move. They are loosely held mobile electrons and they can easily be attacked by electrophilic regions. Now you understand why would they be attacked by electrophilic regions? Because they can act as a source of electrons. These electrons are not very strongly bound. They are a little free to move around. So anyone who needs it will come and break this friendship easily and take these electrons. The pi bonds, and therefore these pi bonds make alkenes unstable. Anything that reacts is unstable, because if it was stable like alkanes, it would have preferred. I couldn't hear what you said. Oh, I wasn't talking to you. So, what was I saying? That anything, the pi bond makes alkenes unstable in comparison to alkanes, and therefore they readily combine. I lost my train of thought, so I'll just read this and explain it to you. The pi bond makes alkenes unstable in comparison to alkanes, and therefore alkenes become more unstable in comparison to alkanes, because in alkanes there were no pi bonds, no electrons free to be released, and therefore they readily combine with electrophiles to form single bonds. So when they combine with electrophiles, the second bond will be broken and both the carbons will get back their electrons and they will combine with the electrophiles, forming a proper bond. So addition reactions will take place. When addition takes place, both the electrons go back and they add the electrophiles to the molecules. Now, if we compare the bond enthalpy, if there is the carbon-carbon double bond, the bond enthalpy, what is bond enthalpy? The energy required to break 1 mole of those bonds. So if you have to break 1 mole of carbon-carbon double bonds, the bond enthalpy would be 681 kilojoules per mole. But if you had to break 1 mole of carbon-carbon single bonds, you would need only 348 kilojoules per mole. So looking at this, you feel that alkenes should not react, because it is more difficult to break the bonds in alkenes, but it is easier to break the bonds in alkanes where there are carbon-carbon single bonds. But this is where it is misleading. In alkanes, you are expecting the 2 carbons to break off completely. But in alkenes, this is a combined energy of 2 bonds. The first bond has an energy of 397 kilojoules and the second bond has an energy of 284 kilojoules. So it is this bond which is going to break. So the 397 is still greater than the 348. The bond enthalpy of the first bond is still greater than that of alkanes. But the second bond is weaker and therefore it is the second bond that breaks and participates in chemical reactions. The 2 carbons do not get separated. Only the second, the pi bond, will break and result in chemical reactions. And that is why alkenes are more reactive than alkanes. So with this, I'll end this video. We'll study more about alkenes in the next video. So I'll wrap up this video right here. If you found it helpful, please give it a thumbs up, subscribe to my channel, recommend it to your friends, and please keep returning for more videos in chemistry. Thank you for watching and bye-bye for now.